welcome to Matter Over Mind. So this is a podcast that explores physics and psychology. Thomas, so
Hello.
Welcome back. Hello, Thomas.
Hello, how's it going?
Yeah, very, very good. So we've got two more episodes actually, haven't we? We're going to talk about God, big topic, and we're going to look at it from a physics perspective and a psychology perspective. And as normal, we're releasing them as dyads.
Yes.
You know, I'll just keep on going with this.
it'll hit off eventually.
Just, you know, yeah. Do you know what? All podcasts will do this at some point.
Yeah,
and then they'll say, "Where did it come from? This idea?" And they'll say, "It was us." Yeah. Anyway, so yeah, we're going to release them at the same time. So when you're listening to this, there's another one that you can listen to about psychology. So we're going to, I mean, obviously these overlap a bit, which is why we thought it'd be quite interesting. So there might be some obvious overlaps that we might get into, but we're going to mainly try to focus on the physics bit today. And I suppose you've prepared some thoughts on this, but what we're looking at, you know, the arguments, I suppose, for God, a creator, and for and against, I suppose, and we're looking at it from this physics perspective, this science perspective first. So we're going to do that today. And obviously, as a physicist, I'm guessing you've come across these thoughts, at least some of them, and some of these arguments.
Yep.
So yeah, where do you want to start?
So there's a few sort of main ones that crop up quite a lot. But I suppose the sort of cosmological argument is probably a good place to start. So this is this argument sort of goes a little bit like, there was a Big Bang, which is sort of considered the beginning of the universe, the start of the universe. And because there was a start, something had to have got it going, right? So what happened before the start? So this is kind of this idea that there was a higher power that began the universe, from the beginning. So this is sort of this idea.
Okay.
Yeah.
So this is an argument that I would have used. So our listeners may or may not know, those who've listened to my other podcasts will know, but I was raised in a fundamentalist Christian religion. So I was very much in this sort of side of the court where I would say, yeah, you know, if there was a beginning, there has to be an original cause. So what happened before the Big Bang, if the Big Bang indeed happened, and actually certainly my brand of fundamentalism believed in the Big Bang. So that matched the belief in a creator, because it's easy for you to say, okay, well, who made the Big Bang happen then? And people like you know, physicists and people just have abdicated that argument for many, many years. And so, yeah, what's your thoughts about that then?
I mean, I could understand the logic behind it, right? I mean, the beginning of time, kind of, we live in time. So experiencing anything outside of it kind of doesn't really make any sense. So I can kind of sympathize with that thought. But, I mean, yeah, I guess the point that I'm not going to try and prove or disprove any of these comments here, because we don't really know, right? But I'm just going to sort of talk around the subject a little bit. So, I guess to talk about the Big Bang a little bit, we need to understand sort of expansion. You know, so the Big Bang happened and the universe is expanding. We kind of touched on this in our episode about the shape of the universe, but I'm going to come at it from a slightly different point of view. So, in the previous episode, I mentioned about curvature, and whether the curvature was open, closed, or flat determines how the universe will expand or contract, and so on. But I'm going to come at it from a little bit different. So here, we're thinking about it in terms of densities. So this is imagine you've got the universe. It has a set density. So this is the collective density of the matter that exists in our universe, the radiation that exists, and this sort of dark energy, dark matter term. So those three things together, when you add them up, you get the universe's density. And is compared against this term called the critical density, which is basically, it's a term it's a value that determines how the universe will continue to expand. So in the event that our current density, or rather the density of our universe, is equal to this critical density value. What that says is basically the universe will expand up to a point where these values equilibrate, and then the universe kind of stagnates. It stops expanding. It doesn't collapse or continue. It just kind of stays there. So this is analogous to the I think it's the flat universe argument. So yeah, it kind of expands and then kind of just stops. So that's that one argument. Another argument is if suppose our density is greater than this critical value, then we'll kind of endlessly expand forever. And then there's the other one, which is the sort of recollapse argument. So this is one if you have, for example, negative curvature, or in this case, less than this critical density. We'll expand to a point, and then we'll sort of start to recollapse. And there's ideas here that supposing you're in a closed system, so supposing there is nothing outside of our universe, so that all the energy and whatever else in our universe have to remain constant. There's no reason to say that once we begin recollapsing, once we get to this sort of infinitesimal size, another Big Bang will happen, and there will be in this endless loop of expansion, recollapse, expansion, recollapse. And again, assuming we're in what's called the closed system, there's nothing in physics that kind of prevents this. That we're not breaking the laws of thermodynamics. Entropy is still conserved and all that. All the stuff that you would kind of consider. So perhaps the Big Bang was the beginning, or it could have just been one of the events in this sort of cyclic collection of expansions and recollapse. So I guess that would be somewhat of a counter to what was the beginning. Well, in this case, there wasn't really a beginning. Where's the beginning of a circle, right?
Okay, that's interesting. So, so yes, what came before the Big Bang, the answer to that would be another Big Bang, essentially. So this is a continual cycle of Big Bang, universe expands, and then it contracts again, and then, or I think Roger Penrose talks about the idea that if the universe expands forever, or in an infinite way, then at some point, because everything is so disconnected, if you like, and I guess there is nothing there anymore, effectively it becomes another sort of singularity in the sense that it then bangs again. So it's not like it crunches, it's just that it keeps going, and at that point to say that there is a universe is kind of meaningless. That's when the Big Bang happens again. I don't think many people understand what he's talking about, but we talked about that. But it is one of his theories, so yeah, it just reminded me of that. Okay, so I guess that's an argument. Yeah, okay, against, does it have to be God? Well, not really, because it could be this circular thing that happens over and over again. Yeah. Okay.
Yeah. I mean, I suppose you could then argue, well, what caused this sort of infinite loop to happen? I suppose then you could kind of extend God created that, right? So there's not really any ideas, but just in terms of Big Bang being the beginning, that's not necessarily true. It makes sense because we are in our current phase of expansion, but maybe not. I mean, other arguments also have kind of come up that sort of say, the Big Bang that we're part of isn't the only one. We could be in a local pocket of the grander universe, and there are many of these things going on. In which case, because we only can see the observable universe, right, which is the 13.8 billion light years across or whatever it is. But yeah, we could just be a small bubble in a sea of other bubbles. So there's nothing inherently special about our universe. So I guess that could also be somewhat of a counter.
And I think it's worth at this point just making the point that neither of us are philosophers. So I guess we get into philosophy if we're trying to prove or disprove God's existence. Then in many respects you get into philosophy, and neither of us are philosophers, and I guess neither of us particularly want to be philosophers. So there'll always be an argument for and against whether God exists. What we can do is talk about it from our own field the expertise we've got in our own particular area. So you're limited by things like physical laws, what you can observe, what you can infer from observation, what you can test, and what you can do mathematically. You can always say, yeah, but what about outside of that? So a philosopher has always got that trick up their sleeve.
Yeah.
And we can't really say anything about that. So if you really want to believe in God, if you believe no matter what, well, that's fine, isn't it? No one can prove that there is no God for definite, because how can you prove a negative? So so I think it's just worth saying up front, we're not going to be proving one way or the other. What we're trying to say is these are the questions that a physicist thinks about when they are asked about that question, and then on the next one we'll think about what a psychologist might think. So okay, what else are we thinking about?
Okay, so that's sort of this idea of critical density and whether we're greater than or less than that can sort of dictate how we expand. And this sort of leads into then the sort of apparent fine-tuning argument. So obviously with critical density, or with just density of the universe, we need to measure things. We need to understand the speed of light and gravitational constants and so on and so forth. So this idea, this fine-tuning, basically says, and the main proponent of this was a guy called Martin Rees. So he's a cosmologist. I mean, there's a theme. A lot of the people that come up with these arguments are themselves cosmologists. So he had a lot of influence when it came to researching the Big Bang and quasars and that kind of thing. So he had, he's a reputable scientist.
I know. I've seen him talk about this.
Yeah, and he wrote this book called Just Six Numbers. And here he kind of outlines. Now, I'll like to preface, I've not read this book, and this is just a quick search of what the book. But he says that there are basically six numbers that if these values were slightly different to what they are actually, what we measure them to be, then the universe kind of wouldn't exist in the way that it does. Therefore, it seems like you'd have to have some kind of architect behind the scenes tweaking these values such that we can exist today. So a few of these, I'll sort of read them off the list. So, for example, the number of dimensions we live in spatially is 3. We've got the sort of average dark energy density of the universe is this value. 0.68. It's kind of normalized, so that value doesn't really mean anything. Or, the fraction of mass converted to energy when hydrogen and helium is fused is about 0.007. So that obviously matters when you come to stellar formation and all this kind of stuff. So the numbers he lists, basically, these values were different. A lot of the early universe stuff kind of wouldn't have been able to take place, which means we wouldn't really exist in the way we see now. But there's one value that he doesn't, well, I say one value, there's many physical constants he doesn't mention, but the one I'm going to talk about is the fine structure constant, because this one I find kind of interesting, and also with it seems interesting to non-physicists in a way that kind of fits with this argument. So this
is this the one over 137?
Yes, exactly. Yeah.
Right, okay.
So this value, this fine structure constant, it was discovered or defined to quantify something called fine structure. So I'll explain that in a little bit. But it's a collection of physical constants that appear a lot in sort of electromagnetism and quantum mechanics, and yet it approximately equals 1 over 137, which is an oddly specific fraction for this constant that appears a lot of times in physics. And this kind of also fits in with the other fine-tuning stuff. It feels too specific for it to just be coincidence. 1 divided by 137 kind of feels a bit strange. But yeah, so what this is called, a fine structure constant, or sometimes a Summerfield constant. And it quantifies a fine splitting in atomic physics. So basically, you'll remember, because I go on about it all the time, with electron orbitals, with energy levels in quantum mechanics, you have these shelves, right? You've got, a ball has to be on one shelf or another one. It can't lay in between i.e. the ball's height on these shelves is quantized. You can only be on one of the shelves. So that's fine when you look at the sort of basic picture of quantum mechanics. That's the position on which of these shelves is called, the principal quantum number. But when you start to look a little bit deeper, particles aren't just billiard balls with set energies. They have, spin and angular momentum and a bunch of other quantities. So what you get is, instead of having just nice shelves spaced as they are, you have subshelves. You have a fine structure or a splitting of these shelves, where depending on the spin of your electron, you'll be, shelf 2 plus a little bit or minus a little bit. So you kind of sit in between shelves just by a small amount. So yeah, that was kind of initially where this term came from, to quantify this fine splitting. But it turns out it might have a more sort of fundamental, I guess, property, that it, in sort of quantum field theory, it quantifies the interaction between the electron and the photon field, or the electric field. Yeah, so it quantifies how strongly the electron interacts with the electric field and sort of more generally the photon field. Now that probably doesn't seem too much more fundamental than the other thing I mentioned, but electrons are come under a class of particles called leptons, which are said to be fundamental. There is no smaller constituent in the lepton class than electron or muon or whatever. Unlike, protons are made of quarks and stuff, electrons are the fundamental.
Fundamental, yeah. Okay. Yeah.
Similarly, you could argue photons are fundamental. There's nothing really that makes up a photon. It is just a packet of electromagnetic radiation. So how electrons interact with light, or more generally the electric field, dictates a lot of dynamics, a lot of the stuff. So I've got written here. So a lot of electrical circuitry sort of uses voltages or potential differences to make the current flow. You use a battery, you've got a positive and negative node on your battery, and that sort of sets a potential difference to allow the current to flow. The voltage basically is the force that accelerates electrical charge, and it does this via the electric field. So this quantity, how electrons couple to the electric field, kind of dictates how electric current flows. It also dictates how we see a lot of light. So the photoelectric effect, for example, this is one where if you have a bit of metal, if you shine a particular frequency of light on that metal, the photon can kind of kick out an electron of this material, which then itself can also set up a current flowing. So this is actually what won Einstein the Nobel Prize, this photoelectric effect. And again, it doesn't seem that interesting. You shine a light on a surface and it emits electrons. But actually, this was sort of the foundation to prove quantum mechanics existed, because it shows you have this quantization effect of light, and then how you can have a packet of light effectively equaling this ionization energy of your material. So how the electric field interacts with electrons, or how light interacts with electrons, kind of dictates how we see, how we interact, how we can even see things, how electrical circuits behave, all this other stuff. So it's a very fundamental parameter, which is why it comes up a lot. And yeah, it's got this strange form that it's equal to about 101 over 137, which seems very specific and a little bit fine-tuned.
Yeah. Okay, so this is one of the strongest arguments of the fine-tuning argument, that we couldn't be here if things were just a little bit different. You've talked about those 6 areas that Martin Rees identified, and now there's this other one which is called, what was it called?
The fine structure constant.
The fine structure constant, which is this number 1 over 137. So I came across this on my YouTube, rabbit hole journeys that I sometimes take, and it's people get very excited about this, and I think that's really interesting, because I know we're not talking about psychology today, but it feels to me like there is a psychological element to this. Why is it that number sounds so interesting? It's kind of almost like I was watching a life story of Douglas Adams the other day on on TV, a documentary about him, which is fascinating. Douglas Adams, the author of The Hitchhiker's Guide to the Galaxy, and of course his number was 42.
Yeah.
So the computer is asked what is the answer to the meaning and purpose of life and everything, and the answer there is 42. And in a way, that's kind of like the same thing. It's like, oh, that's the number. And then when you think about it again, you think, well, okay, well, so what? What? Of course, the question was, what is the question? That's okay. If that's the answer, what is the question? Because it's the question that really matters.
Yeah.
And yeah, that there is this constant in the universe. The other thing that I guess I at some point wanted to throw into this conversation is again another Douglas Adams quote, which actually helped me a lot when I was battling with my own sort of decision about should I carry on believing in God or not. And that was, he said, imagine if by some strange quirk of fate that a puddle on the road, a puddle gained sentience. So suddenly this puddle became conscious. Imagine it saying to itself, it's a really good job that I'm in this shape that is just right for the hole that I'm in.
Yeah.
If it wasn't for this shape, I wouldn't be able to fit in this hole. And it's like, well, actually, that's the wrong way around. Obviously, you're that shape because that's the hole that you're in.
Yeah.
And I think that sort of thinking that got me. It was really one of the very first things that got me thinking. Well, that's the problem with the arguments for God around the fine tuning. Of course, it used to be for the Earth. So when I was younger, the argument was, if the Earth was just a few 100,000 miles closer to the sun, or a few thousand miles closer to the sun, we'd boil. If we're a bit further away from the sun, we'd freeze. The Earth is just right. This is one of the major arguments for why the Earth was created by God. But then, of course, when you realise that there's literally billions of planets out there, all different distances from the sun, it starts to think, well, okay, so one of them's going to be this distance, and then the other one is we've evolved to fit the conditions that exist, not the other way around. So we evolved to suit the conditions that are here. I think the fine-tuning of the universe argument is another variant of that. Now, they would argue that it's not quite the same thing, because if that number was even a little bit different, 1 over 125 or something, then not only could our type of life not exist, but no form could exist, so matter wouldn't be able to do what it does. And obviously you can explain the physics, but those things are fundamental to actually anything existing. And so that's the counter argument now, I think, from the creationists. And of course, another argument coming back is that actually, well, if we've got multiple universes, if the Big Bang isn't just a single instance of it, if there are these continual Big Bangs, or if we're just one corner of the greater universe, then again, you're back to the same question again. You're back to, well, actually, that just like the Earth isn't unique, it just happens to be in a good place for life, Goldilocks zone, if you like. We could be in a Goldilocks universe. So I think it's a very interesting. Again, we can't really prove it one way or the other, but I think this idea that just because this number crops up a lot means God, I struggle to accept that argument.
No, I
don't know what you think.
I mean, I definitely agree. I mean, it's do we exist because these numbers are the way they are, or are these numbers the way they are, therefore we exist? I mean, it's a kind of subtle difference, right. But I mean, coincidences exist, right? I mean, that's why it's hard for us to create random number generators that are truly random, right? Because randomness.
It's like saying in English that thank goodness the letter A exists. If we didn't have the letter A, then we couldn't have English. Well, okay, but it would be something else, wouldn't it? It would be a different language without the sound A. And it would still we could still communicate. We'd still have a language. We'd still be able to do that. So the fact that we don't have, an imagined letter, I don't know. I'm trying to make up a random sound now, but I can't, obviously. But it's as I say, the fact that we have this thing means that the language evolves and changes and adapts, but with the restrictions that are currently in place. So yeah, but nevertheless, it is fascinating that we have these constants. So yeah, I find it fascinating, and okay, it's not a terrible argument, but it's not a humdinger. It's not the one that says right, okay, this is a proof.
Yeah, exactly, definitely. I mean, yeah, it's certainly cool, but things are the way they are. And then,
Exactly.
that I suppose kind of leads on a little bit to this sort of the matter-antimatter imbalance, which
Yeah.
this perhaps isn't necessarily an argument for or against God, but this kind of crops up in this sphere of discussion. So this is obviously we mostly exist in a world full of matter and not antimatter. Because if there was equal amounts of matter and antimatter, they would annihilate and we would be nothing. We would just be a sea of energy. So why is there more matter than antimatter? So to kind of explain a little bit what annihilation is here. So this is this is a unique process, I suppose, when you have a particle and antiparticle pair. So an antiparticle has exactly the same properties, identical properties to its corresponding regular particle pair, but with opposing charge. So we know if two opposite charges, they attract, and because they have identical properties, they what's called annihilate. So this is the only process in physics that has 100% conversion efficiency from mass to pure energy. So this is E equals mc squared. So the E is the energy, and m is mass, and c squared just allows. If you remember back from episode 1, way back when, if you have a massless particle, it has to be traveling at the speed of light. So that's why the speed of light appears there. So this is actually E equals mc squared as a reduced form of the full expression, but this is kind of rest mass. This is the easiest one. So basically, yeah, it's the only process in physics where you have a complete conversion from mass to energy. So yeah, you have a particle-antiparticle pair. They attract each other because of their opposing charges, and because they are identical in every way, they annihilate and produce a pure energy output. There's no excess material. It's just all turned into energy.
Energy.
So yeah, as a result, if when the universe was created, we were equal amounts of matter and antimatter, well, all the antimatter and matter would annihilate, and we wouldn't have anything anymore. So it's pretty lucky that someone decided to remove most of the antimatter, leaving us with a material universe. So this is kind of an interesting one. And again, there's not really any answer. This is one of the kind of big questions in cosmology is why? Why is there this imbalance? So I'm going to indulge myself a little bit. Given there's no correct or wrong answer, I'm just going to start talking.
Okay. Go for it.
So I guess first off, how do we even know antimatter exists, right? We're made of stuff, so why is there anti-stuff? So it kind of comes from the fact, I say comes from, this is kind of how we know stuff exists outside of our regular material. So we know that there exist vacuum fluctuations. So this is the case where you have complete empty space, there's nothing there. In a classical description, you can have an empty space, a volume with nothing in it. But in quantum mechanics, you can't have this. There's always what are called 0 point energy or vacuum fluctuations. And this is basically you can't have nothing in a quantum world. There's always this sort of quantum fluctuation brought about by the uncertainty principle, the Heisenberg uncertainty principle. So I'll explain that in a second. But so we've proven these fluctuations exist, these vacuum fluctuations exist via something called the Casimir effect. So like a lot of things that I mentioned in these podcasts, there is loads of caveats. So I'm just going to break it down real simple. So essentially what happens here is the experiments that they've shown this Casimir effect is that they put two plates, two charged plates, very close together, and these plates experience a force, and this force can only exist. It's either an attraction or repulsion, depending on the specific setup of the experiment. But they basically show that this force can only exist due to pressure exerted by these vacuum fluctuations. So they can prove in a lab that there are these quantum fluctuations that do exist, and they can exert a force on materials. So that proves you can have vacuum fluctuations, which probably seems kind of pointless. Like, who cares? But the cool thing about this is if there are fluctuations in the vacuum, that means there isn't ever a true ground state. There isn't ever a zero energy state. There is always some energy that exists. And this is because of the Heisenberg uncertainty principle, or rather the Heisenberg uncertainty principle can explain this. So there's kind of two forms. One of the forms that often is thought of is the one where if you know a particle's position, you can't know its momentum, or if you know its momentum, you can't truly know its position. There's an uncertainty, depending on which one you measure. And if you the only way you can know its position is if you basically stop it, at which point you've collapsed the wave function, you've destroyed any quantumness. But the other form is from an energy picture. So you can have large amounts of energy that exist from nothing, essentially, from these vacuum fluctuations, providing they exist for a correspondingly short amount of time. So it doesn't sound like it's the same thing, but it's just a different picture of seeing the other uncertainty principle that I said. They're exactly the same thing. But essentially, yeah, so you can have energy that kind of blips out of nowhere. It just spontaneously exists, providing it, the higher the energy, the shorter amount of time it can exist for before the universe notices, and then it has to kind of equilibrate. So a consequence of this is you get these virtual particles forming. And virtual, I don't mean virtual in the sense of they don't really exist. I mean virtual as in, for a particle to exist, you need a lot of energy. And if E equals mc squared, the speed of light squared is big, so you need very large energy to have mass. So these virtual particles, they're called such because for a short amount of time, because of the uncertainty principle, you can have a large spontaneous amount of energy form, and if the energy is large enough, you can create particles, but they always form in particle-antiparticle pairs. So when they form, they immediately attract each other and annihilate, go back into energy, and then the universe kind of balances itself out in that corresponding time scale. Cool. So again, experiments have been done to this, and antimatter has been found from this way. And you can see them if you Google anything to do with bubble chambers. So they don't really use bubble chambers anymore, but this is a sort of historical way of how they did particle physics experiments. And in terms of what is in the bubble chamber, I'm not too sure, it's some medium. But you can see the tracks left by particles streaming through. And if a particle has charge, it'll spiral. So an electron will spiral, say, leftwards. I'm not too sure specifically the direction, but suppose it spirals leftward. If an anti-electron or a positron is created, it will spiral in the opposite way. Or rather, the opposite charge spirals in the opposite way. So you can see these tracks, basically, and you can kind of say, oh, this tightness of spiral indicates it's an electron. Oh, this other thing, though, is spiraling exactly the same way, so it's got the same properties, but it's in the other direction. And then I guess you'll see if they attract each other and then turn into photons, you'll know. Cool. Okay, so again, this probably seems like a meaningless comment that I'm just making. But suppose now, I'll come up with this hypothetical. Suppose now you have a particle-antiparticle pair created just through spontaneous fluctuation in the vacuum. But this happens very close to the event horizon of a black hole. So the event horizon here is the point of no return, the point at which if you go beyond, you fall into the center of the black hole. Fall in is not correct, but for argument's sake, you're attracted to the singularity. So if this particle-antiparticle pair kind of form on this boundary, Well, one of them is going to fall into the black hole. It's going to cross the event horizon, which now means it basically doesn't exist in the way we think.
Right.
But now you've just got a stray particle or antiparticle just traveling through space, not annihilating, therefore not equilibrating with the universe. And this sort of idea led to the idea of Hawking's radiation, which is basically the decay of black holes, this sort of ambient radiation that gets given off by black holes. It actually comes across in something called the Unruh effect, which basically means if you're an accelerating reference frame, you observe this ambient thermal background, which there's a bunch of intricacies there. But essentially, if you're accelerating near a black hole, you can see spontaneous creation of particles versus a stationary observer. Again, not quite, but basically. But yeah, so this is kind of this thing. Because either particle or antiparticles fall into the black hole and the other one hasn't, to equilibrate, the black hole needs to then start decaying to balance out the equation. So suppose for a second now, and this is now full just complete speculation, suppose whatever the Big Bang was, suppose you can treat it somewhat like a singularity, and you have just ambient particle-antiparticle in complete balance, constantly annihilating each other and spontaneously forming again. Then the Big Bang happens, and a collection of matter that happens to be localized falls over the boundary that is now the Big Bang, and then the rest of it's left outside. The rest of the antimatter is left outside. So now you've got a case where you've got inside the bubble that is expanding of our universe, you've got the matter, and its corresponding antimatter's outside now. Now, obviously, this is just me kind of making stuff up, but it happens with black holes where you get this, you get an imbalance occurring because something's fallen into this gravity sink and the other one's flown off. So you can have the case where a particle and an antiparticle don't necessarily
get separated.
Exactly. So suppose maybe this, the Big Bang behaves somewhat like a singularity, and if you fall in, you're trapped now. But the other stuff now can't access it, perhaps.
So in your analogy, we're inside the black hole, essentially.
Yeah. And it happened to be that a collection of matter fell in before it could annihilate, and then now it's trapped.
That's where the matter is. That's really interesting.
Like I said, there's no evidence whatsoever for what I've just said. This is just complete speculation.
It's just conjecture, but I mean, why not?
Yeah.
We're a podcast. We're not a seminar. It's interesting because the whole, obviously not the bit at the end, but the question around. Sorry, did you say vacuum fluctuations?
Yeah.
The whole thing around. I remember when I was a fundamentalist Christian, I was one of Jehovah's Witnesses, which many of you will know, which involved knocking on doors, trying to convince people to change their religion or go and get one if they don't have one. And I remember I was always interested in science, so I was one of the ones that was always pushed to the doors where people were, oh, this one is a bit of an evolutionist, you go there. So I that was my job. And I remember knocking on this particular door, and this guy, he was trying to explain this to me. He spoke about, quantum physics. If first time I'd ever heard really of quantum physics. So we are going back a long time. I've been left like 30 years, so it's a long time ago. But I remember him trying to explain that to me. If you have actually something can come from nothing. So, if you have this, what you might think is nothingness, then things can pop into existence. That's quantum physics tells us that. And of course, I just smiled arrogantly and explained to him, who was obviously somebody who knew what he was talking about. But I explained to him how design requires a designer. The very word creation, creature, means that we must have been created. So I think that's really interesting. It is something that was raised with me very many years ago, but again, because of my own beliefs, that I just didn't have the right way of thinking at the time to make sense of it. It sounded just nonsense to me at the time. Yeah. So I don't know whether that's not really relevant, but it just kind of reminds me of a conversation I had many, many years ago and leaves me feeling perhaps a little embarrassed. But I didn't know any better.
Yeah, well, I mean, yeah, You're found the light now, Stephen. So it's all...
Found the light. Yeah.
yeah. But
Yeah,
yeah,
literally. Okay, that's really interesting. Lots of interesting stuff there. Okay, so is there anything else that is kind of relevant to this topic around God and physics?
yes. There's one final one, which,
Okay.
in my opinion, this is the weakest of all the arguments, and
Okay.
it's a bit of a pet peeve of mine that perhaps you will
Okay.
share. And anyone who's watched anything of Sabine Hossenfelder will know
Yeah.
exactly what I'm
So
talking
she's a
about.
YouTuber that we've spoken about before.
Yeah.
So yeah, go for it.
So this is the mathematical neatness argument, or the neatness brought about through mathematics, and this essentially says that because we can describe the physical world with mathematics by these neat, tidy expressions, it's too tidy for it to not have been designed. And this is kind of the argument of, is maths discovered or created, kind of thing. So it's a nice idea. However, my kind of argument for this, or rather against this, is we use maths as a tool to describe how the universe behaves, but it isn't the universe itself, right? So I guess in the same way, pieces of paper with words on them, they're required to tell a story, but are they the story itself? If that makes any sense, right? Or is it the ideas that are kind of you need them? You need some form of communication to tell a story, whether it's written or verbal or visual. But is that medium the story? I suppose, right? Maybe this doesn't have an answer. Maybe this is more philosophy, but it's the same.
I'm going to put my oar in here. I think you're asking a really, really interesting question. We said we're not philosophers, but hey, again, it's our podcast. We can do what we want. I think this is a philosophical question, but I think this one's quite easy to answer personally. So if you've got a story about my first day at school, and you write this story on a piece of paper using whatever language you choose, you are, as you said, you're telling a story using a medium. But that itself is not your first day at school. It's a story of your first day at school. It's that old "this is not a pipe"
yes,
picture. So we have to be careful we don't confuse the map with the territory, as somebody else once said. I can't remember who said that either, but so the story, the medium, the map, these are just models. These are representations that help us to understand the actual experience, not the experience itself. So yeah, I think that's a really good point.
Yeah, and it kind of like, often you kind of see this, the Fibonacci sequences. Oh, there's the spiral. You see it a lot in, the shells of snails, or how the sunflower seeds grow or whatever. And there was a great quote by Neil deGrasse Tyson. He basically, someone brought this up to him in a podcast, almost as like an intelligent design kind of argument. And his response was, well, yeah, it does appear in those things, you're right. But also it doesn't appear in so much more stuff. You're kind of ignoring the stuff where the Fibonacci sequence isn't seen. Again, with the sort of fine-tuning argument, it could be there because there's this mathematical underpinning of everything, or it could just kind of be coincidence. Or, it could just be efficiency thing, right? So, I mean, honeycomb forms in these hexagonal structures, right? But apparently the bees make them cylindrical, and then when the wax gets heated up, they kind of form this efficient shape. There's a few other examples, but it's essentially the path of least resistance. The universe wants to minimize the energy it takes to do a thing, and we talked about this when we spoke about Lagrangians a few weeks back. So it could be intelligent design, or it could just be the universe wants to minimize its energy. You could argue it wants to minimize its energy because there's a creator telling it to waste less energy, or it could just be that's how.
And this is the problem. It could be anything, couldn't it? So it could be the universe itself. So maybe the universe is the intelligence. Maybe it's that, or it could be. So one of the things, I think, one of the main questions that a lot of creationists come up with is, why is there something rather than nothing? And there needs to be a first cause to whatever, however you want to describe it. There's always got to be a first cause, and so again, we are saying that because all of our experience requires that. So we live in a world where there is always a cause and effect relationship going on. So we're just so used to that that's all we've ever known. But if you're willing to imagine a God who sits outside of everything we know, then why can't that just be the same but for a non-personal God? In other words, why does it have to be an intelligence? Why could the first cause not just be something that is not intelligent? Why does it require intelligence? And that's, for me, one of the big problems. It's like every argument you have for God is also an argument for something else. As I said, you could imagine, and some philosophical beliefs like Buddhism, for instance, doesn't really have a personal God. So everything that you said that points to a creator could also be said for the Buddhist idea of the universe, or the natural order of Taoism, or whatever sort of other way of thinking you want to come up with. It doesn't require this God that is so much in our culture. When people talk about God, they're thinking of the Christian God. Most of the people we talk to, anyway, are talking about that God. But yeah, it doesn't have to be a personal God at all. It could just be whatever that first cause was. Or if you're thinking about time as endless, then maybe there is no beginning, as you said. Maybe there's no beginning, like there is no beginning to a circle. That's really hard for us to get our head around. But you have the same problem with God. So if somebody was to say, well, okay, well, what's the first cause? What came before the Big Bang? Well, it's part of an ongoing series of Big Bangs. Yeah, but what caused that? You've got exactly the same problem with God. So where did God come from? Well, God's always been here. Okay, same for the universe then.
It's
It's exactly the same problem, and I will not accept anybody that tells me it's different unless they come up with a better argument. So if you're coming up with a better argument, then fine. But just by saying, well, there has to be an intelligence behind it. Well, why? Why does there have to be an intelligence behind it? If you're saying that God has always existed and there is no beginnings to God, well, why can't that be the case for the universe? It's a massive mystery. Our puny little minds cannot comprehend it. But just like a devout Christian would say, our puny little minds cannot comprehend God's eternal nature. What's the difference? Explain to me the difference, please.
Yeah, I do certainly agree with that, because before the universe, maybe there's nothing before God. That's not really a question people.
Yeah, same question. And I'm not saying there is no God, because I think it's impossible to know the answer to that. I think we have to work on the assumption that if there is a creator, then that creator is not giving us the answers to all these big questions. So we've got to get on with it and find the answers ourselves. And that's what physics is for. That's what understanding the mind is for. That's, we're on that journey trying to understand this thing that we exist in. It's mind blowing and exciting, because we have this opportunity to try and understand as much as we can. And I think that's why it's better to have that stance than, we don't need to worry about that because God created everything. It's all a mystery. We don't need to worry about how he did it. He just did it. And so, all praise God. Well, that takes away any interesting, what's the point then? Just do what we're told. We're getting into religious and theological arguments now. But is there any more physics, or is that it?
And that's pretty much it. Basically, those are the sort
Yeah.
of the big ones that come up.
Mm.
And like I said, we've not really tried to necessarily disprove them. Just give my
Mm.
thoughts on them. Some of
Yeah.
them are stronger than others. Like I say, I mean, in my opinion, the mathematical neatness is probably the weakest of all
Mm.
the arguments because it's just a bit,
Yeah.
yeah, a bit. It's just yeah. But the cosmological one, what's before the Big Bang? It's a fair question. The fine tuning again, I think, is kind of weak, but also who knows, right? But yeah, so that's kind of yeah. This will never be answered. There'll never be an answer to this question. So
Mm.
I guess
Yeah. That's right. And so the question is, what do we do then in the meantime? And I think I've sort of already said what my assertion is that we assume that um, we don't have a creator who's going to give us all the answers to this stuff. We need to find out for ourselves.
yeah,
If there is a creator, then that creator has on purpose let us try and find out the answers. Now I know religious people would point to their holy books, but even if you take these holy books as books written by or inspired of God, they're very limited in what they tell us. So it seems to me that if there is a God, and even if this God is one of the gods of one of these holy books, then that God has purposely left out a lot. And so I think it's incumbent upon us as human beings to say, right, okay, well, I'm going to find out all the stuff we don't know, and so let's
yeah,
do it. And if we hadn't have done that, we wouldn't know anything about the universe really. So that's what we must do. We must find out, we must understand, and we need to follow the scientific method in order to do that.
yeah,
If you want to believe in God, that's absolutely fine, but we still need the scientific method for all the stuff that God doesn't tell us about. So let's focus on that.
yeah.
That's my kind of
Agreed.
philosophy.
And there's obviously these are the big questions, but there's a lot of interesting
Mm,
physics we still really have no idea about.
that's right. Yeah.
So stopping here because yeah, we don't know what happened before the start of the universe is a little bit silly because, like you said, there's a lot
Yeah.
of stuff that yeah we haven't been told or hasn't been found out yet. So
And
it's
we have
always
a
cool to
we
know
have a
more.
choice. Yeah, we have a choice then. When I was reading again, going through my period of testing my own faith and reading about what different points of view were, this whole God of the gaps thing started to become really obvious to me. So, before we understood anything about the stars and the greater universe, we thought that the Earth was the center of the universe, that the sun revolves around the Earth. That's what we thought was happening. Um, and then there were other mysteries. So I don't really understand what's happening there. These bodies don't seem to behave in a way that we'd expect. Well, just don't worry about that. That's a mystery. That's a celestial mystery. Now, if we'd have said, "Oh, okay, let's not worry about that," then we'd have just we never would have found and understood that actually the Earth revolves around the sun and we have other planets in our system, and comets are this and that, and we would never have understood all those things. But as soon as we understand those things, then the God of the gaps pops up again. So currently, it's quantum physics is where the God of the gaps sits.
Yeah.
So that this is where people who must believe in God say, "Oh well, God, that's the bit in there because your science can't explain how this works or that works. So that must be God." And then over the years, we learn more about it, and that the God of the gaps sort of has to then retreat into another place. And in a way, I think the last hiding place for the God of the gaps is right at the very beginning of the universe when,
Yeah.
yeah, we're never going to be able to get past that particular barrier. So that's God's last stand is there, right there. But it's not been a great record of a way to understand the universe. Science has helped us to understand the universe in a way that religion never has.
Yeah.
And even when religious people like monks and so on started to understand about the universe, they did it through scientific endeavor, not through interpretation of scripture. So
yeah,
for me, that's we've got to do that.
For what you're saying, it kind of seems like with science, it's guilty until proven innocent. You have to.
Yes.
Whereas with the God, it's the opposite. It's innocent until proven guilty, which obviously you can't prove the negative. So it's kind of but yeah, like you say, it's a nice point to set up your last stand before the Big Bang, because who knows what happens, right?
It's impregnable. We're never gonna be able to prove that there was nothing before that, or that God wasn't responsible for that. So, and no matter what proof people like yourself, physicists, might come up with to explain how the Big Bang occurred, or even if there was a before the Big Bang, any of that doesn't really matter, because there'll always be, but what about before that? Or what about outside of that? There's always a hiding place, but it's become there have become fewer and fewer gaps for God to hide in. I mean, as I said, I'm not a strong atheist in that I don't claim to say that there cannot be a God, because I don't know. And we said right at the beginning, no one knows for sure.
Yeah.
And that's fine, but we have to operate on the basis that God's not going to step in and save us. Neither is he going to explain everything to us about what's happened. So if he's there, if she's there, if it's there, leaving it to us. So we need to get on with it.
Indeed. Yes.
Cool. All right. Well, I've enjoyed that. And so next one, by the time you listen to this, it should already be there ready for you to listen to, which is the one around psychology. So what I want to talk about on that episode is the why do we seem to have this this need, at least some of us, to have a belief in God, and is it good for us or is it bad for us, and how does that affect our thinking and psychology? So because I think it's undeniable that there's a spiritual dimension to pretty much all cultures, so clearly there's something going on there. So we're going to explore that, and I think that's going to be quite an interesting one.
Yeah.
Okay. Wait. Well, thank you very much, Thomas. I've really enjoyed talking to you about that. Listeners, please tell somebody about the podcast. So, go on your favorite little app, WhatsApp or Signal or whatever it is that you use, and just send a little note to a friend and say, you should check this podcast out. And that would be great. So we've had some nice little comments recently on our Facebook page, so you can join our Facebook page as well. So shout out to Haywood Gatch, who gave us a lovely little comment recently, so thank you for that. And let more people know, because obviously that's going to determine whether we come back. So we are planning the second season, and probably the odd bonus in between, but for now, don't forget to like, subscribe, and do all the good social media things you need to do. Thank you. Bye for now.
Bye.